Okay, I think now it's recording, right?
Mhm.
Okay, you should receive it. A message telling you that I'm recording.
Yeah, if you want, we can start and just check eventually if somebody joins.
Okay, so let me. Okay, so let me share my screen. Okay. Okay, you should be seeing my screen now. Can you confirm?
Yes.
Okay, so let's start. So first of all, I would like to thank Luis for his invitation and also for the effort to organize this short workshop. And also thank you. I see some familiar names like Ryohei, and I really thank for using our navigation system. It's really it's kind of an honor for us that you are using our navigation system. And Luis asked me to have this workshop, maybe in order to explain some parameters that could be kind of not well explained in the code. So I hope that these slides will help you to better use the navigation system. And first of all, about our team. Well, we have been participating in At Home League since 2006. Actually, you can see here Luis in Eindhoven, but not this Eindhoven, the previous Eindhoven in 2013. Also here, maybe you can see Luis over here. This was our participation in Istanbul in 2011, and we have been participating in many, almost all editions except for the after ones after pandemic. First participation, I was not in the team, but our first participation of the team was in Bremen in 2006. So I think we have gained some experience in the RoboCop at Home League. And about our laboratory, I think maybe Luis tell you has told you more about our laboratory, but we are located in Mexico City, in the university city, in the School of Engineering. Here are a couple of photos about our campus. And in our laboratory, we develop, of course, the domestic service robot. Our main project is this robot that we call Justina. But we also develop some other kind of robots like the humanoids, biped humanoid robots. We also have an HSR robot of Toyota. We only have one, and we have the B version. Hope we have more in the future. We also develop some algorithms for self-driving cars, but only in scaled models. But we have achieved some good algorithms. And this is our laboratory, and particularly the navigation system was part of my my reports, what I did in our laboratory, and really thank you for using the navigation system. So let's start with the theoretical part. First of all, if we are talking about the motion planning problem, let's say that motion planning problem comprises several subproblems. The first one is the navigation, and although navigation is used as a synonym of the general motion planning problem, actually navigation only comprises the path planning and the path following and obstacle avoidance. That's the problem of navigation, and of course, part of the motion planning problem are also mapping and localization. So what is navigation? Is basically pathfinding, path following, and obstacle avoidance. Mapping, it's building an environment representation. What's an environment representation? Anything that is useful for decision making. But we'll be using a particular kind of maps, and localization is determining the robot's current configuration given a map and a set of sensor readings. And as maybe you know, the localization and mapping problems are usually solved simultaneously in the so-called problem of SLAM, the simultaneous localization and mapping. First of all, we need for motion for planning movements, we need an environment representation, and these representations could be of several ways. There are indoor maps, there are outdoor maps, there are geometric maps, there are topological maps, there are semantic maps, probabilistic maps. But the ones we'll be using will be only indoor maps, are kind of more easier representations, since usually indoor environments are all flat and full of straight lines, walls, and geometric features. There are also many ways to represent indoor maps. The most common one, I think, is the most common used in the at-home league. Are the occupancy grids. So formally, what is an occupancy grid? It's just a discretization of a space in which for each discretized cell, we assign an occupancy level. Theoretically, it's a value between 0 and 1. But in order to avoid an excessive use of memory, of computer memory, we used an integer between 0 and 100 to require only 1 byte to represent this level of occupation. And in a probabilistic approach, this p-value this probabilistic value represents the uncertainty we have about the occupancy level of the cell. So for example, we say, okay, a cell has an occupancy level of 1, we are completely sure the cell is occupied. If we say it's 0, we are completely sure it is free. We say 0.5, we don't have information about the occupation level, we don't know nothing. But in general, we only use the binary values 0 and 1 just to represent free and occupied space. And one of the first things we need to do for a map to be useful for path planning is to inflate the obstacles. And these are reasoned really simple. So although there are some spaces where there is no obstacles, not all the free space can be used by the robot, and the reason is very simple. It's because the robot has a size, so it's not a point. The robot has a given size. So there are some parts of the map that, although there are no obstacles, the robot cannot be physically there because of the size of the robot. So the first thing we need to do is to inflate the map to get to mark these places where the robot cannot be. Okay, here is an example. The white cells are the free space, black cells are the occupied space, and gray cells are free space, but where the robot cannot navigate. So we need to indicate that these cells are not available for the robot. And maybe the question is, why not just to modify the original map? It's because we need the original map to perform the localization. Map inflation algorithm is really simple. It's just can be solved with this couple of forms. If you want to use another library, inflation is a morphological operator known as dilation. So many libraries like OpenCV or other libraries have already an implementation of this morphological operator. In our navigation system, we use our own inflation algorithm. Actually, this is the algorithm implemented in the navigation packages. And there are also some other ways of representing the environment. Apart from occupancy grid, we can use also, for example, just line segments. Maps built with only line segments. It has the advantage of not requiring require much less memory, but there is the difficulty of finding the lines. Previously, in our navigation system, we used this kind of maps, and they were useful. But nowadays, I think the best option are the occupancy grids. Some other options for representing environment are for example, the generalized Voronoi diagram. For what we can do, we can use the generalized Voronoi diagram. For example, for finding those points, those cells in the map that are equidistant to the two nearest obstacles. So if we find the Voronoi diagram, we find the cells that are the most safe cells for navigating, and we can use it for path planning option, for path planning also. And well, now, what is path planning? Path planning consists just on finding a sequence of points, points belonging to the set of 3 points that allow the robot to move from one configuration to a goal configuration. So it's very simple. Just to make a clarification, there is a difference between path and trajectory. We plan paths, not by the moment. We don't plan trajectories. We only plan paths. That is, we only get sequence of points to reach the goal, but these points does not indicate any information about speeds. Okay, and when we parameterize a path with respect to time, then we get a trajectory. So we get also profiles for speed and usually also for acceleration. But by the moment, we are only planning paths, not trajectories. Okay, and there are many methods for planning paths. Some common methods are the sampling-based methods and the graph-based methods. There are also others, are optimization methods. There are many others kinds of algorithms for planning paths. But the most common ones are these ones, the sampling-based method and the graph-based. Sampling-based methods, as the name says, are based on a random sampling of the space, hoping for finding straight lines to reach the goal point. And as we take random samples of the space, we build a tree until the goal point is reachable, usually by a straight line. But we can say we find the goal point if we can reach the goal point with a simple movement. So with a simple behavior, we can reach the goal point. Then we say we found a path. The most common algorithm is the rapidly exploring random trees, and in the literature there is a lot of variation of this algorithm, varying the kind of sampling, varying the starting point, varying the criteria for adding or not a node to the tree. So there are many ways. This is an example of how we can build the tree. So we just take a lot of samples until we can build a tree for reaching the goal point, so we can plan a path. At the end, also we build a graph, and also we need a graph search-based algorithm to plan the path. But first, we build a tree using some random sampling. Okay. And of course, the method we use in our navigation system is a graph-based method. By the way, if you have some question, so feel free to raise your hand, and I think it will be more interactive if you make any question you have. Thank you. And the graph-based methods are methods that consider the space as a graph. This is reliable only for certain map representations, and the occupancy grid is a very, very good map representation for consider as a graph. And in the graph-based methods, we say that each free cell in the occupancy grid is a node in the graph, and this node is connected with all free neighbor cells. It results in a very big graph, but the finding is it's really fast, so it's not time consuming. And the general steps for this kind of algorithms can be summarized in this algorithm. Let me summarize it. We have two main sets, which we call an open list and a closed list. Open list is what we call also a frontier. So it's the set of nodes that we are not sure we have found an optimal path, but it's the set of nodes that were candidates to be expanded, candidates to be to calculate an optimal path. And the closed list is a set of nodes for which we already know the optimal path. And of course, if the closed list is the set of nodes for which we already know the optimal path, when we add the goal node to the closed list, so we can say we are done and the algorithm has finished. And the graph-based methods have the big advantage of being complete algorithms, which means if the solution exists, the algorithm for sure will find the solution. And if the solution does not exist, the algorithm for sure will terminate infinite time. So this is very useful for planning paths. And the common steps are, okay, let's add the start node to the open list. And until the open list is, while the open list is not empty and we have not reached the goal point, what we do is just to choose a node from the open list under some criterion. And we will see that selection of this criterion will result in the different versions of the graph-based methods. And we remove this node from the open list. We add it to the closed list. So when we add a node from, to the closed list, it's because we have already found the optimal path for this node. And we expand the current node. What do we mean by expanding? It's just checking the neighbor nodes and adding them to the open list. And we say that the selection of the criterion for choosing the current node from the open list results in different versions of the algorithms. So for example, if the criterion is the FIFO criterion, so we get the breadth first search algorithm, and the open list is a queue. So if we follow the LIFO criterion, so the algorithm will be the depth first search algorithm. And in this case, the open list is a stack. And Dijkstra algorithm, for example, uses as criterion selecting the node with the smallest G value. So what is the G value? It can has different meanings, but we can see the G value as an accumulated cost. So Dijkstra will give us an optimal path, and optimal in the sense that we minimize the G value. And A star also uses, well, in the case of Dijkstra algorithm, the open list is a priority queue. So it's a queue, but with priority, and the priority value will be the G value. And A star algorithm is the one we are going to use. It's very similar to the Dijkstra algorithm, but it's an informed algorithm, and the criterion will be the smallest F value to choose the following node to expand. And there are some similarities between the different algorithms. So for example, if the cost G from one node to another is always 1, then the Dijkstra algorithm just becomes the breadth first search. And also A star and Dijkstra will always calculate the same path, and the difference is the time for calculation. So Dijkstra can calculate paths for multi-goal. So it's a multi-goal algorithm. We can find paths for many goals, while A star not. A star can calculate an optimal path, but for just one goal, but with the big advantage that the searches are faster than the external algorithm. And in this point, it's important to say that Dijkstra and A star minimize a cost function. That is, the calculated paths will be optimal paths in the sense that minimize a cost function. And usually the most common cost function is the distance, but can be also maybe the travel time, the total number of turns, the consuming energy, among many others. So what we do for navigation in our package is to build a cost function that is a combination, a sum, between traveled distance and risk of collision. How do we measure risk of collision? It's just the nearness to obstacles. So the nearer the road are to an obstacle, the bigger is the risk of collision and the bigger is the cost. So if we take this combination as a cost function and we get optimal paths under this cost function, we will get paths that are both short and safe. So, for example, in this image, the red path is shorter, but because it travels very near to the obstacles. So although we inflated the map, this is not a really safe path, so that the robot has more chances to collide. And the blue path is a larger one. So it's a larger one path, but it's safer. So, if we take as cost function the sum of distance and risk of collision, the blue path is the optimal one because minimizes both distance and risk of collision. And this is the cost function we use for planning paths. And that's why the robot can move through safe paths. So that minimizes the risk of collision. How do we calculate these cost maps? It's very simple. We establish a radius for calculating the nearness, and we just establish integer values to the cells around the occupied cells, indicating how near we are to these occupied cells. So in this example, for example, in this small map, we are calculating a cost for only 3 cells away from the occupied cells. And we just assign an integer indicating how many cells we are far from the obstacles. So this will be the cost map we'll be using for optimizing paths. So all paths will have a total cost, okay, of the distance traveled plus the nearness to obstacles. And that's why the A-star algorithm will find paths that are both safe and short. So, so what is the A-star algorithm? Maybe many of you are familiar with it. It's a complete algorithm. We said before. That is, if the path exists, the algorithm will always find it. Otherwise, it will terminate in a finite time. And same as Dijkstra, A-star finds a path that minimizes a cost function. The cost function, as we said before, is the sum of the distance traveled plus nearness to obstacles. That is a measure of risk of collision. Okay. It's a kind of informed search algorithm, which means that uses an estimation of the remaining cost to reach the goal for prioritizing the expansion of certain nodes. So if we have several nodes with the same accumulated cost, we will choose the one that has less cost for reaching the goal point. And we need only an estimation. We cannot have the exact remaining cost because we will know the exact remaining cost until we execute the search algorithm. But we need an underestimation. Okay, so this heuristic function needs to underestimate, okay, the remaining cost. And usually, if we are navigating through a 2D space like our robots in the common spaces, we can use a heuristic function. The best heuristic function is the Euclidean distance. And since all distances are positive and all these costs are always positive, okay, Euclidean distance is always a good heuristic since it will always underestimate the remaining cost for reaching the goal point. And this is the F value, is a combination of the heuristic plus the accumulated cost. And this F value is the criterion for selecting the next node to expand, okay? And this is the A-star algorithm. It is already implemented in our navigation package. I think it's not worth to review the whole algorithm. Let's just say that for optimizing the search, we need to implement the open list as a heap structure. So in this way, insertion of nodes n will be done in logarithmic time, and selection of the node with the least F value will be performing constant time. So because if we use a common array as an open list, we can have a very, very big execution time. Okay, so using a heap structure is important for making the A-star algorithm to run faster. And also, since we are using an occupancy grid, selecting the neighbors of a given node can be done in two ways, using 8 connectivity or 4 connectivity. Yeah. So if we use 4 connectivity, we will always have only orthogonal paths. Yeah. And if we use 8 connectivity, we can have the diagonal paths. Okay. And depending on the connectivity we choose, we should use a different distance function. Euclidean distance can be used always, okay? But for example, if we say, okay, we are going to use 4 connectivity, we can use Manhattan distance, which is a little bit faster to calculate than Euclidean distance, okay? So maybe at the end, the user will not notice the difference in time, but we can save some time if we use the correct distance function, okay? And, okay, and well, I think the examples of the path calculation will be shown in a few minutes by Luis. Okay. So by the moment, let's say that if we already have these paths that are calculated, that are planned by the A-star algorithm, okay, the next point, well, is to calculate the control laws to make the robot to follow the path. Okay. So for path following, okay, we will design some control laws. Okay, that is, we will design functions to calculate the speeds of the road to follow the path. Okay, and of course we will calculate these control laws on their several assumptions. The first one, of course, is that we know the current road position, which of course it's a big assumption because calculating the position of the robot is not a trivial problem. Okay, but we will see later that we can use many algorithms to calculate the robot's current position. Okay, we will also design these control laws under the assumption that the kinematic model is enough to model the robot's movement. So, what does it mean? That we are ignoring a lot of dynamics, such as the electric part of the motors, the mechanic part of the motors, and we just consider that the electric part and the mechanic part of the motor and in general the actuators are fast enough to be ignored, right? So we will consider that the kinematic model is enough to model the robot's movement. Okay, and although most of us have omnidirectional bases, okay, for moving the robot, we will design our control laws considering only a differential base. And there are several reasons. The first one is that the differential base is the easiest configuration due to the simplicity of required hardware. So we don't need, for example, omnidirectional wheels. So I think we already have experience in this. Building an omnidirectional base it's more complicated than a differential one. Differential base is really easy to build. Okay, and although this kind of differential basis implies a non-holonomic constraints, which mean a non-holonomic constraint. It means that the robot can only move in one direction in a given time. So in a given point of the time, in a given instant, the robot can only move in one direction. And this direction is, of course, the direction of the tires. Okay, the direction of the wheels of the robot can change over time, but in a given instant of time, the robot can move only in one direction. So this is a non-holonomic constraint, and it's a non-holonomic constraint because there is no constraints on the position of the robot. So the robot can reach any position in the space, but cannot move with any velocity. So the constraint is only on velocity, not in position. That's a kind of constraint called non-holonomic constraint. And although these kind of constraints imply some difficulties for making the control laws, we will assume this configuration of mobile base because it's the easiest one, okay, to build, and also with a very practical reason. And it's basically because we all have robots with the sensors pointing to the front. So the cameras don't point to the sides of the robot. The cameras point to the front. The laser one also points to the front. So it's useful that the robot always move to the front. So that's why we build control laws considering only a differential base and not an omnidirectional one. And the position control we use is this one. Okay. Let's see. Okay, the equations maybe look a little confusing, but that's really simple. These are the graphs generated by these equations. This V is the linear speed of the robot, and this omega is the angular speed of the robot. And we are calculating it as a function of something we call the angle error. Okay, so what is the angle error? Is just a measure of, just tell us if the robot is pointing or not, okay, to the goal point, right? So let's say this is a graph of the linear speed, and okay, let's clarify something. What we are doing is that if the robot, I'm very sorry, I just noticed that I didn't change to English these captions of the figures, but let me tell you. Okay, this is the shape, okay, of the function generated by this equation. And what says this graph is if the angle error is 0, that means if the robot is pointing to the goal point, okay, the robot does not need to turn. The robot only needs to move in a straight line. So that's why if the error angle is 0, okay, the linear speed is big and the angular speed is 0. So if the robot is pointing to the goal point, the robot does not need to turn, only needs to move in the straight line. And as the error angle increases, even positively or negatively, when the angle error increases, the linear speed decreases. And when the angle error increases, okay, the angular speed also increases. So what does it mean? If the angle error is big, so the robot is not pointing to the goal point, then the robot will not move to the front and will only turn. And as the robot approaches to the goal point and points to the goal point, so it will start to move to the front and stop turning. And that's just what these control laws do. Okay, there are some tuning constants. Some of them are given by the physical capabilities of the robot. So Vmax and omega max are the linear and angular maximum speeds that are that the robot can reach, and of course are bounded by the physical capabilities of the mobile base, but we can also set it to save speeds. So for example, in the at-home tasks, we usually set it to at least 0.5 meters per second and not more. And also the turning speed, the angular speed, we usually set it to something less than 1 radian per second. Okay. And alpha beta are just some tuning constants that tell us how fast the linear and angular speeds change with respect to changes in the angular error. So in general, small values of alpha and beta will make the robot to follow the path more accurately. And we can say, okay, but let's just set alpha and beta as small as we can. But two small values of alpha and beta can make the robot to chatter. Okay, so to make this kind of oscillations, and very small values of alpha and beta can also damage the hardware because of the chattering. Okay, and big values of alpha and beta produce smoother movements, but can result in very extensive curves. So alpha and beta will big values of alpha and beta will make the robot to move smoother, but can also make the robot to move away from the planned path. So can cause that although the planned path avoids obstacles, a bad tuning of alpha and beta can produce that the robot moves away from the path and collide with obstacles. Okay. And also, we said before that we are planning paths, not trajectories. So we are not parameterizing the path with respect to time. But yes, it is convenient to have a speed profile. So because we don't want the robot to just start move to the maximum speed, and we don't want the robot to just brake abruptly. So we need a profile speed for making the robot to start the movement smoothly and accelerate, okay, until reach a maximum speed. And we also want that the robot decelerates, okay, before reaching the goal point. And we can make these profile speeds by adjusting, for example, high degree polynomials, or by making, I don't know, B curves or splines or many other techniques. But in our navigation system, what we do is implement just a finite state machine in which what the state machine does is just increment, okay, it's just increment the current, this constant of the equation, that is the maximum speed, is incremented as the robot moves until reaching a max speed, a cruise speed. And when the robot is approaching to the goal point, we just start to decrease, okay, this speed, and the robot will start to brake until it reaches the final point. So let's say this state machine will generate this kind of profile speeds. So let's say, for example, our A-star algorithm calculated this path, okay? And if this is the path, okay? If we use only these equations for moving, okay? This will be the linear speed. And as we can see, the linear speed changes very abruptly, okay, from 0 to the maximum value. And also this means that the robot brakes, okay, very hard from the maximum speed to 0 in a very short time, okay. But if we use this state machine, okay, for calculating the maximum speed of the robot, we can see that we start in 0 and we accelerate, okay, in a constant acceleration until we reach, okay, a cruise speed. And as we approach to the goal point, we will calculate this maximum speed. Okay, so here we can see that the robot is decelerating, okay, until reaching the goal point. So the robot stops. Okay. And some extra step about path planning is the path smoothing is a post-processing step for path calculation. Okay, because since we are planning paths using occupancy grids, okay, occupancy grids have corners, and since we're using A-star and occupancy grids, the resulting paths will always have corners, okay, but corners are not desired, okay, corners are not good for planning, just because corners usually represent discontinuous functions, okay, and this can cause big changes in the control laws that can lead to damage in the actuator. So if we do not smooth the path, we will not note, okay, the changes in the control laws, the changes in the actuator signals, but in time, sooner or later, okay, there will be some small damage in the actuators. So it is always better to have small changes, okay, smooth, okay, changes in the path in order to have also smooth signals for the actuators. So in this example, okay, the green path is the resulting path with A-star, okay, but the one we want is the blue one, okay. There are many ways, okay, for making this smoothing of the path, okay. For example, we can use splines. It's kind of an algorithm for adjusting polynomials, okay, given a set of points. The most common ones are the cubic splines, which adjust, as the name says, third-degree polynomials. But what we are using in our system is path smoothing with an optimization approach, okay? what we're doing is to design a cost function and then minimize, okay, that cost function so that the resulting path, okay, is a smooth path. So let's say this is our cost function, okay? The black dots, okay, are the original path with corners, is the path calculated with a star, okay? And the blue points are the smooth path, the one we want, okay? And our cost function will be, okay, will be in a scalar function, okay? With variables as variables, the positions, okay, of the smooth path. And we say, okay, the cost will be the sum of the distances between one point to another, which are the green distances, okay. And also the red distances will be the distance between one point, okay, and the corresponding in the original one, in the original path, okay. And okay, and what happened with this cost function? If we get, okay, if we get a smooth path, a blue path, very, very similar to the original one, the red distances will be small, but the green distances will be larger. And if we get a very, very smooth path, which could be a straight line, okay, the green distances will be the least ones, but the red distances will increase. So that if we have a very smooth path, the cost function is big. If we have a very similar path to the original one, the cost function will also be big, okay, a big value. So if we minimize this cost function, we will get a path that is not so smooth and also not so similar to the original one. Okay, and we can use these parameters alpha and beta just to adjust the level of smoothing we want. Okay. And how we can find the minimum? We can always calculate the derivative of the function equal to 0 and then solve. But since we have a lot of variables, this can be very, very difficult. So finding an analytic solution can be very hard. So instead, we use a numeric method, which is the gradient descent. And in the gradient descent algorithm, we just move the parameters in the opposite direction of the gradient until the gradient is near to 0, which means we have reached the minimum, okay? This is the general algorithm for gradient descent. So we just move the parameter in the opposite direction to the gradient of the cost function until the magnitude of the gradient is less than a tolerance. And gradient descent finds, okay, a local minimum nearest to the initial guess. But since this function is a quadratic function, okay, we have only one global minimum, okay, and the gradient of the cost function of this cost function can be calculated as this one, okay. So as you can see, it's very, very simple. It's just a function of the coordinates of the points in the smooth path and coordinates in the original path, okay. And this is the gradient descent algorithm, okay? And just to keep the start and goal points in the same value, okay, the first and the last component of the gradient, okay, we keep it as 0 so that the start and goal points does not move. This is the algorithm. Also, we can check it in the code. I think Luis maybe will show later this the smoothing of the paths. Okay, and okay, with this we already have a planet path. Okay, we have an environment representation. We have smooth paths, and we have an algorithm for following the paths. So the last point we can review is how we evade obstacles. Okay, and okay, one of the easiest methods for avoiding obstacles is just to check if there is something in front in the path of the robot. And if there is something in the path of the robot, we just modify the occupancy grid and recalculate A star. But this works very well. But also, if we want obstacle avoidance in a smooth way, we can use this technique, the artificial potential fields. Okay. This is what we use also, for example, for avoiding people when the robot is following up, for avoiding obstacles when the robot is following a person. Okay. And the idea of this technique is to design a potential function. Okay, so this is a function that maps from reals, n-dimensional reals to reals. Okay, such that represents potential energy. So the physical potential energy, but is an energy we design. Okay, such that the gradient of this potential energy is a force vector, and this potential function should be designed in a way that it has a global minimum in the goal point, and such that it has local maxima in every obstacle. So if we move to the point of less potential energy, that it's what physically happens in any movement. If we try to move to the 2 points of minimum energy, so we always move to the global minimum. So we will always move to the goal point, and also avoiding obstacles in the environment. Okay, and potential functions can be calculated in many ways. One way is the wavefront. But wavefront has the big advantage that does not present the problem of local minima, but requires a discretization of the space, requires a map, which is not desirable, okay, because we need a reactive method. And also, we can use attractive and regression fields. With this technique, we do not require a discretization of the environment, and we don't need a previous map, but with the problem that we can have local minima. So this is a really big problem. It's a theoretical problem, the local minima of the potential fields. But if we combine it with some planning with A star, like A star, or we're using, for example, for following people, for following a target, they are very, very useful for obstacle avoidance. So this is an example of how we calculate the potential function. So the rejection field is a potential function, is the center figure, where we have local maxima in every obstacle. The attractive field is an energy field that has a local minimum, a global minimum in the goal point. Okay, and of course the sum of these potential fields is the resulting potential field. Okay, and we will make the robot to move from an initial point, and if we let the robot move always to points with less energy, at some point the robot will reach the goal point, and at the same time it will avoid obstacles, right? So we can calculate the potential functions in many ways. These are the potential functions and the gradient that is a force. Okay, these are the forces that we are proposing. Some features that the potential functions should have is that the gradient, okay, that means the magnitude of the derivative, okay, of the rejection field should increase as we approach to an obstacle, so that the nearer we are to an obstacle, the greater should be the rejection. Okay? And also it is desirable that after some distance, okay, so if we are far enough from obstacles, obstacles should not affect the movement of the robot. Okay, and we can achieve this with these equations. So the attraction has actually a magnitude, a constant magnitude, the attraction force. It's just a vector with constant magnitude, but the only thing that changes is the direction of the vector. Okay, it always points to the goal point. Okay, always with the same magnitude, and the rejection force, okay, is this one. It's calculated. Okay, let's check. This is also a unitary vector, so this unitary vector only points away from obstacles. Okay, and this is the magnitude. Let's check if as we approach, okay, as we approach to the obstacle, this distance is smaller. Okay, So this quotient will be bigger, and of course the magnitude will be bigger. So the magnitude of the reaction force increases as we approach to the obstacle. And if this distance is bigger than this zero, it's because okay, this quotient will be less than this quotient, and we will get a negative value, and we will get an imaginary value. But what we do is, okay, calculate this only if distance g is less than distance of influence d0. Okay, and if robot is farther than d0 from obstacles, then there is no reaction force and there is no influence on the movement by the obstacles. Okay, so these are the variables and the turning constants. Q is just the robot position. QG is the goal position, is for calculating the attraction force. QOI is the ith, okay, obstacle. The position of the ith obstacle is for calculating the reaction force. And the tuning constants are just these parameters, eta, zeta, and d0, okay? D0, we call it as a distance of influence, okay? Because obstacles farther than D0 have no effect on the movement, okay? And this seems to require the position of the obstacles. So according to these equations, we need to know the position of the obstacles in the map. But this is not precisely true because as we can see, we are making the difference between obstacles and the current robot's position. So what we only need is actually only the position of the obstacles with respect to the robot to get this difference. So we can get it with the laser. The LiDAR sensor give us an array of distances. This distance is, of course, this distance. Okay. And we get also the direction of the measurement of the reading, okay, of the LiDAR sensor. So with the direction, okay, the angle of these readings, we get the direction of this, okay, unitary vector. So what we can do is just consider that every reading of the LiDAR sensor is an obstacle. So we are going to calculate, okay, only one attraction force, but we will calculate a rejection force for each reading of the LiDAR sensor. Okay, and with this we can have the potential fields. Okay, so now how do we use these forces? We say that the force is the gradient of the potential function. So we need to move to points with less energy. We need to move to the point of the minimum energy. So what we can do is also move the robot with the gradient descent, okay, algorithm to move the robot through the potential field to reach the point of the minimum energy. So moving the robot with potential fields is very easy. So we start in the start configuration of the robot. We calculate, okay, the rejection force with these equations. Okay, we calculate the rejection force. Okay. And what we do is to move the robot a little bit in the opposite direction. Okay, a little bit in the opposite direction of the gradient. So we calculate a next decided position. And we can use the control laws that we designed previously to move the robot, okay, using this new position, okay, as the desired position, and we repeat. Until when? Until we are close enough to the goal point. This is an example of the movement. Okay, so we have an obstacle. We want the robot to move to the other side of this obstacle. We are drawing here the resulting forces. Okay, this one is the attraction force, the reaction force, the resulting force, and the robot always moves in the direction of the resulting force a little bit. Okay, this resulting force already points to the opposite direction of the gradient. Okay, so that we're using the gradient descent algorithm. Okay. And okay, with potential fields, we can perform the obstacle avoidance problem. And we will review some parts of the localization problem. We are not implementing our own localization problem. We are using the well-known package, the AMCL, the Adaptive Monte Carlo Localization package. But let's review that this is a an algorithm for global localization. That means theoretically, we can set any guess, okay, any guess as the initial estimation of the position of the robot, and at some point, okay, in time, the robot will localize itself. But in fact, it will take a lot of time for the robot to localize if we don't use a very big number of particles, and if we set the initial guess far from the real position of the robot, particle filters will present will be difficult to converge. Okay, then but it's a very good algorithm, and the general steps for performing this localization with particle filters is to generate a set of n particles, okay, generating randomly distributed, okay, move each particle a displacement, okay. So we assume that we can measure, okay, how much the robot have moved, okay. Not exactly, but we have an estimation of how much the robot has moved. Okay, so we have a displacement, not the position, the absolute position in the map, but a measure of a displacement. So we will move each particle. Okay, we will simulate the leader readings for each particle, and the particle filters are very simple, right? So the algorithm basically compares the simulated readings with the real reading. And of course, if a simulated reading is more similar than the real reading, then we have more chances to be in the position of that particular particle, okay? So, and what we do is just to make a resample. We can think that, okay, if we have a measure of similarity, why don't we just get with the particles whose simulated leader was more similar to the real one? And the reason is that we can have errors in readings, and so we can include a particle with a simulated reading similar to the real one, but not because they are really similar, but because an error in the sensing. And also we can have different particles between simulated reading and real reading, not because they are really different, but again, because an error in the reading. Okay. So that's why we take this probabilistic approach, and we compare all particles with the real reading of the sensor. And we don't systematically discard those readings different, okay, with simulated readings different to the real one. What we do is to resample particles with replacement using similarities as probability distribution. And what does that mean? That when we resample a particle, okay, those particles with simulated readings more similar than the real one reading have more chances to be resampled than particles with simulated readings different to the real one. So a particle with a reading different to the real one is not discarded systematically, but just have less chances to be resampled. Okay, and this is the general algorithm. So we have some pictures here. So let's say this is our initial distribution. We move the particles a displacement. Okay, all particles are moved with the same displacement. Okay, we simulate the readings, okay, for each particle, or simulate the sensor. We compare the sensor, the simulated readings with the real ones. The red one is the real one, okay? The red one is the real reading, okay? The blue ones are the simulated readings, so we compare it. Here, the light, the color is, okay? The lighter the color is, for example, this one and this one, indicates, okay, that the simulated reading is more different than the real one, okay? And the more saturated is the color, like this one, it means that the simulated reading is more similar to the real reading. And these particles, okay, have more chances to be resampled. So for example, we resampled this one, although it's not very similar, we resampled it. And for example, this one, although it is very similar, was not resampled. But for example, this particle was resampled 3 times. Okay. And this one was resampled 2 times. Okay. And for avoiding having the repeated particles, which have duplicated information, is not useful. When we resample, we just add some Gaussian noise to each particle so that in the next iteration, one of these particles will have a simulated reading more similar to the real one, and one of these particles will have more chances to be resampled than the other ones. And after several iterations, okay, all particles will converge, okay, to the position of the robot. And okay, there is many other topics that we could cover here in the navigation system. I try to review what I consider the most relevant parts, the most relevant theoretical parts to understand our navigation system. But fortunately, we have no more time. So I just want to thank again, Luis, for organizing this workshop. And I want to thank again, Luis, for inviting me and all of you for attending this small workshop. So thank you very much for attending. And that's all in my side.
Thank you, Marco. That was very nice explanation. I think we solved some of the many questions that you have asked for long. So I will just present how we start the module using a real robot, and then you can ask Marco about all the parameters we have in the launch files and in the files inside the repository. So how can I share my something, Marco?
Okay, let me give you permissions.
Okay.
I think you already
Okay.
have permissions.
Yes. So
Nice.
what do I do? This one. Sure. So I think you can see something. Can you see my screen?
Yes.
Okay, so
Well,
I will
I
continue
do.
to this. Okay, thank you. How we start this. So we have the repository, and you can use it with any robot. And I will review the the navigation launch file and how we started and how all the parameters that Marco explains fit in here. So this is from Hibikino and how they use this repository in the Carry Logage task. So just to show you what's the final goal of this repository. So they are following person using the motion Marco explained and the obstacle avoidance using potential fields. The navigation and path planning using a star and all that, and the obstacle avoidance using vision and navigation. So first we have in the launch file this part that is the hardware. So in the head, we have the repository moves the head for obstacle avoidance, so we need some pan and tilt. Also for navigation to make it look in the motion of navigation as it is required for Robocop. We edited this part to fit with the HSR. So what you need to do is check the hardware head, source, and head node CPP and make your own modifications to use it with your own architecture, with your own robot. In this case, we published to the head trajectory control command and the current pose to check the response. But we are not, it is not a node or a service that the navigation module is waiting for. So you can not initialize it and the navigation system is going to work. But I am just pointing it here that you can edit it to adjust it to your own platform. Also, we have the LED. The HSR has a LED system, and we use it to show some part of the process. We have the current statuses that we have are active, succeed, aborted, and rejected. And depending on the status, the LED info is changed. Again, this is a passive module, so if you don't have it, the system will work. But as we are using some of the HSR libraries, you need to comment those for cat can make them. And finally, the arm, also we use it for the initialization of the robot and to put it in the navigation form. But just in the startup of the navigation module. After that, we don't use the arm configuration any longer in the navigation module. But again, we use the HSR architecture here. So you have a different architecture. You can just edit this and add your own topics. So this is the hardware part that we use for the leg, the arm, and the head. So you need to edit it if you want to use it in your own robot. And also we have for the HSR, we have the killer node and the fake global post to use the Pumas navigation and the Toyota's navigation together. If we don't kill the post integrator, the Toyota's localization system is fighting with the AMSL system in the Pumas navigation. So we need to do this. And we need to republish from the Pumas navigation to global post to be used for the HSR. But this is just a specific file to use this with HSR. So if you have a different architecture that doesn't have another localization system, you can just ignore this part. Then I will not review all of the parameters. For example, in this case, the simple move, Marcos just explains what the max linear speed, max angular speed means, and also the control alpha and control beta for the simple move. So this is for the motion, and the alpha and beta controls the angular and linear velocities when reaching the goal. So I will not explain those, but you can play with those alpha and beta and see what's the different behaviors of your robot. Then we have the static and prohibition map. In this case, those are useful for localization and path planning. In this case, the static map is for localization. We take it with a laser and we don't touch it any further after we have taken this map. Why not? Because if we edit this map, and then as Marco showed in the particle filter, if we change this map and the theoretical value differs from the real value, then the robot will discard the true position, and we will have false positives on where the robot is, and the localization is going to be very bad. So once you take your localization map, you don't edit it in there. What we do instead is to add a prohibition map. So we have a copy of the localization map, and we create a prohibition map, and then we can edit this for the path planning. For example, we can add the tables and chairs that we see in the map, but the laser only see the feet, but we can add all the furniture in there. Also, imagine we have an extra door in the top side of the room, and we have the robot there and the goal point there. So the robot can go in this path, but also if the cost says that, the robot can move in that way. But we don't want if we don't want the robot to go around the house, outside the house, using the different access, we can add some of these extra limitations in the prohibition map. And then the robot will not go to outside. So again, we do all this in the prohibition map. The localization map is never touched because we will have errors in the localization. So make it sure that if you want to add any obstacle, furniture, restrictions in your path planning, you do that in the prohibition map. Then we have this part. In the previous version of this repository, the potential fields node was called obstacle avoidance node, but I just changed the name to make it clearer. So if you download the latest version of the repository, you will have this version with a different name. So in the previous version, it was called obstacle detector node, but I changed it to potential field because it is only used for calculating the potential fields. So in this node, we have some topics that you can edit accordingly to your robot. And we have some Boolean values to if you want to use LiDAR, sonars, or whatever sensor you have. The important one is this one, the use potential fields. This one is going to publish in your topic a result or not, depending on if it is true or false. Also, we have these parameters. This is for making it faster. The downsampling, the point cloud downsampling is to avoid using all the point cloud and make it faster to find all the rejection forces. And we have cloud point threshold and LiDAR point thresholds. Those are to have a minimum number of points that are to be considered an obstacle. For example, in vision, we can have some false positives. So if the obstacle is too small, we just ignore it. Also for the LiDAR, we can have a wrong reading. So if the reading is bad, only one or two, we do not consider an obstacle. Then, well, this is just for visualization. And we have this, Marco just explains what's the potential. This parameter is for the calculation of the rejection force. And this one is for the distance, the minimum distance of influence of the obstacle. So this is something like this in the code. So we use from the center of the robot to the obstacle, we check the distance, and if it is in the influence range, we calculate the rejection force like that. So we have the constant for the potential field rejection force, the K, and we have those distances. This is for the laser, and these parameters we are using the camera, the visual information. So in the visual information, we have only the Z, that is the height of the obstacle, and the distance. We don't use the other parameters in the obstacle avoidance for the potential fields. So we use the distance and the height of the obstacles. And it's similar. We use a scale factor because we want to use the same constant the pot field scale. So we need to scale it to be according to the laser force. So as Marco explained, we have this distance, we have that obstacle. The obstacle is outside of the influence of the potential field. The robot moves. The robot keeps moving, sees the obstacle, and then the robot moves accordingly to avoid this one. If we increase the radius of the influence, we will see the obstacles before, and the robot will move evading this. This is important because we can react to the obstacles before or after we see them. For example, here, in the real world, full with walls, the robot, and with a small distance, the robot will move softly. But if we have this distance parameter too high, we will see the walls as obstacles, and then the robot will reject them. Then we will see here, and then the robot will see all the walls, and then like this, and this is going to be like a ping pong behavior. So here we have to, with a small distance of influence, here we see the robot, and the robot will see the feet of the chair, just on time to react and the reaction. So the robot saw the feet and the motion was smooth, just very close to it. However, if we have the distance parameter in the launch file very high, very large, we will have some behavior. Oh, wait a second. And it's not moving. Let me see, what can I do with this? Because I want you to see this. Sorry. Can you see something? Because I cannot.
Yes. Well, if it is a video, then no. If it is just a photo, then yes.
This is a video, but
I
will.
No, we're seeing a frozen image
Okay, I
on
will
your presentation.
update this. This happens when you use Microsoft software. Okay, let's see if it works now. Okay. So you see the robot will start ping-ponging here. It's the obstacle, the wall, the other wall, everything. So the robot starts doing this strange behavior. So we compare the previous one when we saw the chair just very close and the robot moved, compared to this one where the robot just started ping-ponging. It is because of the distance of influence of the D0 and max X in the visual and laser-based potential fields avoidance. So another parameter of interest, so that one, the potential fields only is aware of potential fields, as the name says. If we need to, Marco explained it very shortly, but we have the map augmenter. In this one, if we see a dynamic obstacle, we can add it here in the map augmenter. The map augmenter is to add dynamic obstacles. So again, we have laser and point cloud based parameters, the cloud downsampling again, and here the inflation radius is what Marco explained, and it is how we expand the map. This corresponds to the diameter of the robot plus some extra distance. So if we add, the inflation radius should be larger than the diameter of the robot. So we can avoid collisions. The robot trying to go to a closer distance to the real volume of the robot. But the cost radius is also important, and it is for the path planning. And I think in somewhere we have, what was it? To disappear the objects.
Which one?
How fast the objects remain in the map.
But the topic,
Dynamic obstacles.
I think it's not listed in your file.
Okay.
It's parameter called let me remember, decay time, decay factor.
Okay.
It's a parameter of the map augmenter node. Maybe you can just add it to your launch file. I can send.
So we can have a decay factor here also, and if we see an obstacle, the map augmenter is going to add it to the map, and depending on the decay factor, it is going to disappear. It is in seconds.
Not really. Okay, that's something we have to improve. It's just an integer, And for example, if the integer is 10, then it will take 10 seconds to disappear because the occupancy level is 100 for a full occupied cell. And so the decay factor is 10, then it will subtract 10 from the occupancy level until reach 0.
Okay. So something somewhere in there is a decay factor. So check it later. And this is interesting. Then we have here, and we use the LiDAR and the point cloud to add obstacles. However, these parameters are both for LiDAR and the point clouds. We don't have a LiDAR max X or max Y. We use it for using this one. For example, for the LiDAR, we have this, and this is in 2D. Well, the 3D, the set is constant, but yeah. And for the cam, we have the same value. So we can add obstacles using this, but we use the same parameters. So this is important because we have the potential fields where we have max X for the influence of the obstacles. And we have the Mach augmented when we have the same parameters for the obstacle detector. So what we need to do to have a better control in our launch is just change the separability. So we need to edit the launch file, and we will have a potential fields parameters and obstacle detector parameters. So make sure you have this separately, and you can have a better control of your robot. I just wanted to highlight this part. Then we have the prohibition map. We publish a constant map. Then this prohibition map enters to a map enhancer, and we can edit this prohibition map dynamically just by clicking it in the RV's screen or publishing in the topic of the robot that is point stamped. So we can publish any point in there, and it is going to be added to the prohibition map dynamically. We have a function to clear it also, so you can add and clear your prohibition map dynamically if you see extra obstacles that you didn't map it before. And every point you click is going to have a radius of 5 centimeters, but you can edit it. And then this the map enhancer is going to publish the prohibition map that is used in the map augmenter and all the path planning system. So we have the publisher there that it enters to the enhancer, and then it enters to the path planning in there. Then we have, it wasn't explained, but we have the leg finder, and that uses the laser and something like that. And then we have the human follower that uses the motion commands that Marco explained. We have the alpha and beta and max linear and max angular for the human follower, and distant to human parameters. As we showed in the video, the robot follows a person smoothly, but we used a 2D leg detector that is very basic. It works, it has worked, but it's very basic because we don't use person re-identification. So we follow any person that moves in front of the robot, but we cannot distinguish between person A and person B. So we just follow a person. So if you want to use any other system that uses some visual information, we use potential fields here in the human follower to avoid the obstacles while following a person, but we just read the potential field node. So you need to start the potential field node before using it here. And you can use it, the leg finder and the following like this. And then as we're saying, the human detector publish a 2D point of the person. And then the human follower reads that. So if you want to use a person detector using your camera, your XTON, or whatever for identification, you can use publish a similar 2D point of the resulting person detector. So you can use RGBD camera, use your face recognition or whatever, but just make sure if you want to continue using the person follower, make sure that you publish it as a point stamped topic and just remap it to this one, and you will have the same behavior using your camera or whatever system you use. Then finally, we can use it using a map that you have previously got. And we have the map server to publish that map, and then the MACL to relocalize. But also, you can use an online system like this one. In this case, we don't start the AMCL because we don't have a map. We are doing Islam, and we don't start the map server because we are doing it online. What we start is a server bypass where we take the map from the cartographer or whatever it comes and publish it as a static map. We have tested it with Toyota's cartographer, also with Gmapping and Hector Slam. So it works in all these platforms. And those are the major parameters I wanted to talk to you. So if you have questions or something, this is now the moment. No, any question? Anybody? Okay, Ryohei.
Thank you for presenting. So, so I have one question. The control alpha and control beta. So I'm not sure about this. So sorry. Please. In control alpha and control beta in the simple move. I think simple moving. So I'm not sure about this. So sorry. So
Okay,
please explain
Marco.
again.
Okay. Let me find. Let me check if I have. One moment, please. One moment. I'm trying to find a figure that could explain this one. I don't know why I don't have it, but I will find it. Just give me a second. One moment, 1 second, 1 second. One second, I'm preparing my figure. So can you see my screen?
Yes.
Okay, thank you. So just imagine we have here a goal point. So we have a robot. Okay, the robot is pointing to here. Okay, and we want to reach this goal point. So first of all, we will calculate this angle error. Okay, this is going to be our angle error. So let's assume the robot is now pointing. Okay, so if the robot is now pointing to the direction of the goal point, the angular error will be 0. And if the robot is not pointing, as in this case, to the goal point, then we have an angle error. So that's the basic variable to calculate the control variables. So again, why we are doing this? If the robot is pointing, okay, is already heading to the goal point, then the angle error is 0, and then the robot only needs to move. Okay, the robot only needs to move in a straight line and doesn't need to turn. Okay, but in this case, in the figure shown here, the angle error is big, so the robot does not need to move, okay, to the front, does not need to move straight. The robot needs first to turn, and until the robot is heading to the goal point, then the robot is going to move to the front, okay? So if we, let me, if we, oh, let's say our goal point is over here. Okay, one moment. So if the goal point is over here, so we have this error. Okay, and okay, we could move the robot with just an if. Okay, so an if else case. Okay, so if for example, if angle error is 0, then move forward. If the angle error is not 0, then turn. Okay, and do not move forward. So if we graph, okay, if we plot the speed, okay, against, okay, this is the linear speed against angle error. Okay, if we plan just an if, we will say, okay, if the angle error is 0, then move forward, and if the angle error is different from 0, then move, then just don't move. Okay, and also we can have the angular speed. So if we plot the angular speed with respect to the angle error, okay, we say, okay, if the error angle is 0, then don't turn, okay? Okay, just move forward, but do not make a turn, okay? Angular speed is 0. And if the angle error is positive, then we have a positive value. If the angular error is negative, then we have a negative angular. But of course, this is not good. So what we are using is a smooth version of these graphs. So instead of having this kind of impulse, we have a smooth version, okay, of this. Okay, and also here we have a smooth version of this speed. Okay, and but how smooth they are. So for example, we can have something very sharp, okay, or we can have something very smooth. So in both cases, if the robot is heading to the goal point, then it will move at maximum speed, and as the robot gets a bigger angle error, it will stop moving forward and will increase, okay, the speed, the angular speed. So I hope this is clear. And angle parameters alpha and beta, okay, determine the shape of these curves. So for example, alpha and beta, very small, it will produce a very sharp plots. So small beta will make something like this. So the angular speed goes to zero very fast and goes to maximum speed very fast. Also, linear speed, if alpha is very, very small, then linear speed goes to zero very, very fast and goes to zero very fast. And also, when the angular error approaches to zero, the angular speed increases very fast. So now, in the movement of the robot, what will happen? If we have a very, very, very fast, a very, very small alpha and beta, the robot will start turning and will move to the front until it's heading almost with no error to the goal point. So the robot will make something like this and will move. Let me use another color. The robot will turn and will move in this direction. And with alpha and beta, okay, big, we will have these smooth, okay, smooth graphs. So with slow changes in linear speed and angular speed, and the resulting path will be something like this. If the robot is heading this direction, okay, the path will be something like this. So red path is a resulting path with a small alpha and beta, and blue path is the path, okay, with a big, okay, alpha and beta. Okay, so apparently small alpha and small beta are always better. But if we use a very, very small alpha and beta, what will happen is that the robot will never move forward, or in any other, if the alpha and beta are too small, the robot is going to start doing something like this. Okay, it's going to produce chattering. Okay, so if you don't mind that the robot goes away from the desired path, you can use small alpha and beta. If you want the robot to follow the path very, very accurately, then you should use small alpha and beta. But too small alpha and beta can cause chattering in the robot. Okay, so that's I don't know if it is maybe clear, or I don't know if I explained myself about this, about how alpha and beta works.
Okay, I got it. Thank you so much.
Perfect. Thank you to you, Rehei.
So any question?
And yes, I have a question. Is it okay to do it now?
Yes, of
Sure.
course.
Okay, so the first question was related to the previous one, where you were saying that the robot usually tries to face the goal at all the time.
Yeah.
And I was wondering what usually happens when there's a goal and you need to do a U-turn. In those cases, the robot is moving, for example, let's say to the right, but need to face to the goal point, which is in the other side, or what is the expected direction of pointing?
I'm not sure if I got your question. So, for example, I think we have two cases of U-turn. So, for example,
Yeah.
we could have a U-turn. Just let's say we have a robot here, okay, and the robot is heading this way, and I think we could have two cases, okay, of a U-turn. We could have a case of a U-turn just because that's the way you plan the path, okay, or maybe you need a U-turn because your path starts this way, okay. In any case, the robot would okay, I got your question. I got your question. The robot will try to find, okay, it will try to head to the goal point, but in these control laws, okay, give me a second. Oh, where is it? Oh, I already closed. No, I didn't close it. I lost my previous Yes, I lost my previous figure. Okay, but yeah, okay. When we were explaining that the robot tries to move. Okay, so this you have a robot, okay, and you have a goal point, and the robot is going to try to head in this direction, but this goal point, okay, this goal point is not the global goal point. What we are doing, this is a position, this is a control only for position control. So the robot is not trying to follow in a path. So this is a position control only. But what we do is try to find one point after another, okay, in the path. So in these control laws, where is my presentation? No, this is not my presentation. Moment. So in these control laws, okay, the goal point is not the global goal point. So the goal point is the next point in the path. Okay, maybe that is what was not clear. So again,
yeah.
okay, yeah. So this goal again, this is this one. Okay, this goal point is not the global goal point, but it's the next point in the path. Okay, so we are going to try to reach the next point, and when we are close enough to this point, then we change, okay, the goal point to the next one and to the next one, and if we are close enough, we change it and change it and change it until we reach the final point. So the robot, yes, tries to head to the desired point, but the desired point changes as the robot moves through the path. Okay, so is this your question?
Yeah, that was my question.
Okay, perfect.
I thought it was the final goal point that was trying to
Yeah,
face all the.
yeah, exactly. But it's not trying to face to the global goal point, but to the local goal point. And actually, here in the state machine that I shown here, again, my apologies for this. I just noticed that I keep some Spanish captions in the figure, but I promise you to translate it to English, and I will forward it to Luis, and I hope Luis can distribute the correct slides. But in this state machine, okay, we try to reach this point, which is the ith point, okay, the ith point of the path. And we move the robot with the control laws. We calculate the distance, this local goal point. And if this distance is less than this threshold, then we change, okay, the point to the next one. If not, we just keep moving, okay, trying to reach this goal point. If we achieve, if we reach this goal point, then change it and change it and change it until we reach the end of the path, and then we stop the robot.
Wonderful, thank you. Also,
yes,
my next question, if it's okay, was related to the obstacle avoidance.
Yes.
I thought that you were sharing that you use a kind of threshold, or let's say an area, a circle area, in order to decide whether to use this kind of a laser distance as an obstacle or not. And when you were sharing the video with the walls, I was wondering if only by reducing the distance or the circumference itself, it may help the robot to move smoother through that path, but it also will let's say to reduce the performance of the robot when moving and maybe eventually collide to the object which is in front of it, or is it working somehow dynamically, changing the area of obstacles around the robot?
Yeah. What we have here is two kinds of obstacles avoidance. One is for path planning that we recalculate the path. That doesn't use the potential fields. The other is the one that I mentioned, using potential fields. And we combine those to have trajectories. In the case of the human follower, we don't use path planning. We only use motion control. And we try to face to the person and have to a minimum distance to that person. We don't use path planning in that case. So we only use the potential fields obstacle avoidance. And yes, you're right. We play both with the rejection force constant because it is too big and we see an obstacle, it is going to push the robot very far. And we start pinpointing as well. And also the influence distance. If we have large distances, we are going to see the walls that we don't want to avoid because they are far. So what we do is play with both, with the rejection force constant and with the influence area. And yes, by reducing it, we can have behaviors like the first video. But yeah, if it is too small, we have the risk to collide with the obstacle. So yes, you need to adjust it with your robot.
I see. Thank you so much.
No problem. So any question? We have like 8 minutes for one or two more questions. Also, you have played with this system and you have more questions on how to configure it, you can just reach me and I can teach you how we use it.
Yes, and also this is my email, so feel free to write me if you have any questions. And really, I'll be really happy to help you with this system. I'm already happy for you for being interested on using our navigation system. Thanks a lot to Luis for making the needed modifications to make it easier to use. So really, thank you. And well, if you have any question, please don't hesitate to write me. And really, I'll be very happy to help you.
So any question? We are recording this, so I will share the video and the slides and everything later, so you can rewatch it. And if you want to modify any of the files and to adjust the parameters, you can do it, and we can help you also we can show you how to do it.
I think Luis also, if I think they can make some suggestions like pull requests on the repository, and I think if we collaborate and we take into account suggestions of all users, I think we can improve a lot the navigation system.
Exactly, that's so. Ryohei has been doing that, and yeah,
I know
we can
that.
just follow Ryohei's path.
I think
Ryohei is an expert in this system, so if you have questions in Japanese, you can reach Ryohei also, and he will answer them very well.
so. Okay, Luis. I think there is another question.
No,
No,
this is a clap.
it's uploading. Yeah, thank you very much. So
Okay, so we can finish.
yes, I
Thank you
think
for joining, and I think there are persons from there were persons for 4 or 5 different teams in Japan, Robocop Japan Open, so we can continue working on this and make some tests, like see if it is better than the one in the Kachaka.
excellent.
So thank you, Marco, for your help and for your time, and it was a very nice presentation, and hope to hear from you soon.
Okay. No, thanks to you for organizing this meeting, and again, thanks to all the attendees. And thank you for using the navigation system. So hope to see you later. And okay, thanks for attending and see you. Bye bye.